And the recording is on. All right. Do you guys want me to go over the topics first, or should we just go head first into some practice problems?
I would like to go over the topics first so we can know what we're doing in the problem.
All right. So let's just go over all the topics. So starting off, we have section 3.3/3.4, which is about arc length and curvature / motion in space. So the first thing that I have on here is know how position, velocity, and acceleration are related for vector valued functions. So essentially, if we have a position function r of t, which is just going to be something, the velocity function v of t, these should be vector functions, is going to be the derivative of the position function, like so. And then afterwards, we also have the acceleration function, which is going to be the derivative of the velocity function, or the second derivative of the position function. So as like a quick little example, let's suppose that r of t is equal to, what's some easy numbers to work with? Let's just go with e to the ti plus sine of tj plus cosine of tk, as an example. Our velocity function would therefore be the derivative of the position function. And to take a derivative of a vector function, it's like taking the derivative of the individual pieces. So in this case, we have e to the ti plus cosine of tj minus sine of tk, as the derivative of sine is cosine, and the derivative of cosine is negative sine. If we wanted to calculate the acceleration function, we'd essentially take another derivative of the velocity, but this time on the velocity function. So the derivative of e to the t is going to be e to the t. So we have e to the ti minus sine tj minus cosine tk, just as an example. And then to find essentially the velocity or acceleration given a position function. Oh wait, we already did it. Oh wait, I already gave you the example. I think you should be able to follow that one pretty easily. And if you're given some values of t, you would just plug them in, or you'd find values of t based on what you're given. Okay, that I think covers position, velocity, acceleration. Unit tangent vectors is next up. So suppose that we had any standard vector function r of t. The unit tangent vector is going to be the derivative of the vector function over the magnitude of the derivative of the vector function, like so. So if I wanted to find it out for r of t is equal to I plus tj plus t squared k, and let's say I asked you to find the unit tangent vector of this function at a particular point, say 1, 1, 1, which should be obvious t is equal to 1 here. So we'd first find the derivative of this. So the derivative of 1 is 0. The derivative of t is going to be 1, so we'd have j. And then the derivative of t squared is 2t, so we'd have 2tk, like this. Now we'll find the magnitude of this, which if you remember the magnitude formula, that's going to be the square root of the individual pieces, and then squared. So in this case, we have 1 squared plus 2t squared, like this, which is going to be 4t squared plus 1. Finally, for the unit tangent vector, we would have the derivative divided by its magnitude. So I'm just going to put a 1 over on the side here, just to make this cleaner, and we have 1 over 4t squared plus 1 times j plus 2tk. Like this. You can rewrite this in any way that best seems fit. And this should be it. If you're given a value, actually I forgot about the value. If we have t is equal to 1 here, we'd have the unit tangent vector at 1. So that's going to be 1 over the square root of 4 times 1 squared plus 1 times j plus 2 times 1k, like so. And that's going to be, this is going to be 4 times 1 squared. That's just going to be a 4 plus 1. So you're going to have 1 over root 5 times j plus 2k. Or 1 over root 5j plus 2 over root 5k as the unit tangent vector of this vector function at the point 1, 1, 1. Okay, next up is going to be the arc length formula, and be able to use it to find the arc length of a curve. Oh my god, the recording. Just hold on. Recording crashed. Just give me 1 second. Should be able to fix this. Okay. So where were we? All right, arc length formula. So the arc length formula is S is equal to the integral from t equals a to t equals to b of the magnitude of the derivative of a given vector function. I'm going to use tau here with respect to whatever the inside is. So I think the easiest way to do this is just by an example. So let's say we have an R of t, which is equal to ti plus 2tj plus 3tk, like this. First, we'd compute the magnitude of the derivative if we want to find the arc. Oh, I forgot to use bound. And suppose we had bounds from 0 to 1 over here. So we first find the derivative, which, if you know your differentiation rules, you'll get I plus 2j plus 3k. The magnitude of the derivative is going to be the square root of 1 squared plus 2 squared plus 3 squared, which is going to be the square root of 5 plus 9, which is going to be square root of 14. And now to calculate our arc length S here, we'd have the integral from t is equal to 0 to 1 of the magnitude of the derivative, which we already have calculated here, to be the square root of 14, dt or d tau, whatever. And then because the square root of 14 is just a constant with respect to tau, we're going to have tau from t is equal to 0 to 1, which is just going to be the square root of 14, as you can see here. See right here. All right, that's it for section 3.3 and 3.4. Moving on to section 4.1, the first of many sections from chapter 4 that will be on our exam. Know what a function of 2 or 3 variables is, how to evaluate it, and find the domain and range. So a multivariable function is just a function where you have, like this, where we essentially have 2 or more variables. So as an example, x squared y is an example of a multivariable function. In this case, we have 2 variables in the input, so we have a function of 2 variables. If I had like f of x, y, z is equal to x squared y, z, this would now be a function of 3 variables, since we have 3 inputs here, giving us 1 output. To find the domain and range, you would do it just like you would any other domain and range question, except when you have the multiple variables, you can often have a region as a domain instead of just simply like a number, a variable, and a number. So as just a tiny little example, let's say we had f of xy is equal to the square root of, I use 16. I'm going to use, let's just use 289. So let's say we had the equation f of xy is equal to the square root of 289 minus x squared minus y squared. So, and we want it, and I told you specifically, find the domain and range of f of xy. So for our domain, obviously because of the square root here, our main issue is going to be making sure that the 289 minus x squared minus y squared is bigger than or equal to 0. Bigger than or equal to 0. So one way we can do this is we can just rewrite the minuses here as pluses, essentially factoring out the negative, like this. And then we'll just add this onto the other side. So we'll have 289 is bigger than or equal to x squared plus y squared, or x squared plus y squared is less than or equal to 289. And I'm just going to tell you right now, 289 is 17 squared. So if we were asked to graph this domain would essentially be all the points where x squared plus y squared was less than or equal to 289. In this case, it's going to be a circle of radius 17. Let me see if I can draw it. Good, oh my god. As you can see right here in the drawing, we're just going to pretend this is 17. This is going to be negative 17 over here. Here, negative 17 and 17. For our range, we want to think about what values can be possibly outputted from this. So from our domain condition, that this is bigger than or equal to 0, we can see that f of xy will also have to output a value bigger than or equal to 0. As there's no other way we have that here. Now, for our range, I want to go back to what we had here, 289 minus x squared plus y squared, like this. X squared plus y squared is always going to be bigger than or equal to 0 because the x squared and y squared are both raised to even powers. Because of that, 289 minus x squared plus y squared is going to be, at the most, 289. Using these two facts, we get our range. Here is going to be 0, z, and then 17, because this was essentially trapped underneath the square root. So our range is at most the square root of 289, or 17. All right. Level curves. So level curves are essentially where you're setting f of xy or f of xyz or whatever to a constant. Here we're going to use k as a constant. Or c equals me. So in this case, let's say I gave you find the level curves of f of xy is equal to, let's go with y over x. Just for demonstration purposes. So essentially what we have here, let's just have a put a graph down. X, Y. So in order to compute out the level curves, we will just simply calculate whatever we get whenever we set f of xy to a constant. So if I just say set z equal to 0, z being f of xy here, we have 0 is equal to y over x. Now, the only way you can have a 0 equals to y over x is going to be if the numerator, in this case y, is equal to 0. We also have to take note that x cannot be 0, because if the denominator is 0, we will have an undefined. So our level curve for the 0 case is going to be the x-axis except for 0, 0 itself, like so, marked in blue. Now we're going to try other values in order to figure out all the level curves. So we're going to try 1. X. This should be fairly straightforward. Y is equal to x. So x, as long as x is not 0, and therefore y is also not equal to 0. So in this case, we have something like this. Again, a hole at 0, 0. And then just going up like so. Z equals to 1. And we're going to do one more. We're going to say that z is equal to negative 1. Set z is equal to 1. Set z equals to negative 1. So negative 1 is equal to y over x. So if we just multiply it by x on both sides, knowing well that x cannot be equal to 0, we have negative x is equal to y, which I'm just going to draw in red, is going to look something like this, again with this hole, like so. Z is equal to negative 1. And this is mostly what you're doing whenever you're going to just try finding level curves and plotting level curves, which is just set your z or f of xy or whatever to a constant, and then figure out what level curve that is going to be by isolating y in terms of x, or however best for you to see the level curves in question. And then that's about it for level curves. Let me just go get up the review again. Okay, there we go. And that's actually it for 4.1. We're only expected to do 2 variables only, so that's it. All right. Section 4.3. This was about partial derivatives. Know and have a conceptual understanding of the limit definition of partial derivatives. So the limit definition for a partial derivative goes as follows. For a function f of xy, the partial derivative of f with respect to x is the limit as h goes to 0 of f of x plus h comma y minus f of xy all over h. Similarly, if we take the partial derivative of f with respect to y, we will get the limit as k goes towards 0 of f of x comma y plus k minus f of xy all over h, like so. So the idea with partial derivatives, at least the conceptual understanding of this, is that we're essentially trying to go closer and closer to a value. Let's say we have a value x naught, but this could be really any x. The idea is that for a certain curve in multivariable, in 3-dimensional space, if we wanted to find the derivative at this point, or the partial derivative with respect to x, we would try to move x closer and closer to x naught like this, and then we are holding the y constant here. So in this case, I just have it over here. This is like your x. This circled out point is like your x naught, y naught. And then whatever we get from the limit definition is going to be essentially the partial derivative with respect to x. Partial derivative of y is going to be very similar. We're essentially trying to go closer and closer to a certain value y, holding x constant. So what does that specifically mean in terms of actually computing these? So let's just find a partial derivative of a function, just to get the point across. So I'm going to say find the partial derivative with respect to x and partial derivative with respect to y for f of xy is equal to e to the x sine y. So for partial derivatives, from what we learned earlier, we're essentially holding the other variables constant. In this case, for the partial derivative with respect to x, we're going to hold the y constant. So in this case, we get the partial derivative of x times e to the x, and because we're treating the sine y as a constant with respect to x, we're just going to put it out front, like out front or behind it, whatever, like this. The derivative of e to the x with respect to x is equal to e to the x, so we just end up with e to the x sine y. We're going to do a very similar thing for the partial derivative with respect to y. E to the x is the constant, and then partial with respect to y of sine y. And this is going to be e to the x cosine of y, like so. All right, let me just see what's... Hold on, let me just go see what's in the chat. Just give me 1 sec. I have no idea why the channel got age restricted. All right, let me just go back to the recording. All right. So where were we? Yeah. So this is this is essentially just going to be a partial derivatives. So let's just do the same thing that we did earlier, but instead of 2 variables, we're going to have 3 variables. Well, I saw something about making the towels look like towels. Oh yeah, they look like towels. All right. So let's say we had f of xy is equal to, let's not use e to the x. Let's say x squared y cubed z to the 4th, like this. And then the question asked you to find partial derivative of f with respect to x, partial f with respect to y, and partial f with respect to z, like so. Partial f with respect to x is going to be doing the same thing earlier. We're going to hold everything else constant, and we're only going to care about the x squared. So we get 2xy cubed z to the 4th. We're going to go through a similar thing for y. I'm not going to do the partial x here like this anymore because I think we've done a lot of those already. So we should end up with 3x squared y squared z to the 4th. As you can see, because the derivative of y cubed with respect to y is going to be 3y squared times the rest of the x squared and z to the 4th. Very similar thing for z. We will just get 4x squared y cubed z cubed. And make that 3 look a little bit better. Okay. So this is the same idea if you're going to try to do this with 2 or 3 or really any amount you want. So second order, or really higher order, partial derivatives. So with higher order partial derivatives, we're going to be using this notation from now on, where to represent partial with respect to x. In this case, this will be partial f with respect to x, because this is just going to be a lot easier to see it. Whereas if we had higher partial derivatives, we'd have to do something like this, which is a little bit confusing and hard to read. So yeah, we're just going to use this other notation. So if fx here, for second order partial derivatives, we essentially just do the exact same thing we did before, but instead of on f, we just do it on the previous partial derivative. So to get a sense for what I'm talking about, let's say we had f of xy is equal to x squared y. And then the exam told you to compute the second partial fxx, fyy, and fxy, like so. So the partial derivative with respect to x twice of f, if we actually start with computing the first one. So the first one, we do the same thing. We have 2xy. The partial with respect to y is going to be x squared. And then to do the partial derivative of it with x twice, we're going to take the fx we had earlier, and then just take another partial derivative with respect to x. So in this case, we're going to have 2y as our answer. As you can see here, if you want, I can just make it a little bit more clearer. 2x like this times y, which is just 2y. Very similar with fyy, where you're just going to take the partial with respect to y, and then just take it with respect to y again. Of x squared. So x squared here is a constant with respect to y, so we're going to get 0 from this. fxy. Here, we're going to just take, here based on the way we have it written here, we're going to take fx and then take the partial derivative with respect to y. So in this case, we're going to take the y here, and then the 2x is just a constant multiplied to it. So we're just going to get 2x. Now, it's somewhat common practice that we only need one of the two mixed partials, as mixed partial derivatives are going to be the exact same. Like this, at least for second order partial derivatives, like so. So that's why I didn't give you fyx, because this would be just twice the work for really the same thing. Though if we were to do it anyway, we'd have the partial derivative with respect to x of x squared, which would have also given you 2x, as you can see here. And it's mostly the same idea if you're going to have any other partial derivatives like this, where you have third order or more. Very similar process to what we did here for the second orders. Though I'm not sure if this fully holds. I think it does. Does fully hold even for third order. But you're welcome to just check that. All right. Though it only asks for 2 variables, so I don't need to do 3 or more. That's going to be 4.3 right there. Section, I'm going to make that a little bigger. 4.4. This one's about tangent planes. And they only have tangent planes here. They don't have linear approximations for this. So, tangent planes, which is essentially a way of approximating a function at a certain point. So let's say we had a curve like this. We could have a tangent plane, as you can see with this massive box here, that essentially just approximates the function at this point, say x naught, y naught, and z naught, like so. the formula for these tangent planes, as described in our lecture notes, is going to be z is equal to pi of xy, which is equal to fxy, x naught y. I'm going to use x naught y naught z naught for this. Actually, no, it is z. Pi of xy, which is equal to f of x naught y naught, plus the partial derivative with respect to x applied at x naught y naught times x minus x naught, plus the partial derivative with respect to y at x naught y naught times y minus y naught. This is going to be our formula. Did I make these too close? Yes, I made this too close. Yes, I'm going to put that right over there. Okay, that is going to be mostly it. If you want you to essentially find this at a certain point x naught y naught, you just plug it into the formula as shown here. So yeah, I'm just going to go through one example of this, and then we'll just move on to 4.5. Find the tangent plane to the function, or of the function, should be f of xy is equal to, what's a good function to put? Good. I'm just going to use x plus y. I don't care. At the point 1, 1, 2, which is specifically chosen because z is equal to f of x. Z at the point 1, 1, which is equal to f at 1, 1, is equal to 1 plus 1, which is 2. So this is the correct f of xy here. So in order to find the tangent plane, we're just going to go first find the partial derivatives. So partial derivative of this with respect to x is going to be 1. And the partial derivative of y is also going to be 1, as you can see over here. The other variable is held to a constant, so it just becomes 0 in this. And so fx at the point 1, 1 is also just 1. Same with fy. It's just a 1. So our tangent plane is therefore 2, which is our f of x naught y naught, plus the partial derivative applied at the point, time, which is just 1, times x minus 1, because we have x equals to 1. Here, pretend this is your x, y, and z, x naught, y naught, z naught. And then we're going to have 1 times y minus 1. This would be your tangent plane over here. All right, on to the chain rule. Section 4.5. All right, so the chain rule for one independent variable to start. Suppose we had f of xy, actually just f of xy, where x was also a function of t and y was also a function of t.
A question earlier was,
Yeah?
Can you make t more curly at the bottom?
Yeah, I think I saw that one. I think they should be fairly curly. The towels here.
No, the regular t's.
Oh, the regular t's.
They look like pluses sometimes.
Okay, let me just go make those a little bit more curly. Yeah, just someone else read me the chat since I cannot see the chat very well for some odd reason. All right, there's curly.
Thank you.
No problem. Let me just go back to here and then. Oh wait, there was no t's on this one. All right, so suppose we had f of xy, and then x and y were functions of t. The partial derivative, actually not the partial derivative, the derivative of f with respect to t is going to be equal to partial f partial x times dx dt plus partial f partial y times dy dt. Like so. So let's just have an example of this just to illustrate what we have. Suppose we had f of xy is equal to x squared y, where x is equal to 2t and y is equal to t squared. And we wanted to find df dt using the chain rule, and only the chain rule, because there is another way to do it here in this situation, but we're going to try to use the chain rule for this. So using the chain rule, we have, I'm going to make these a little bit more curly. So we have partial f with respect to x. So in this case, partial f with respect to x is just going to become 2xy times dx dt, which is just going to be 2, plus partial f with respect to y times partial dy dt, which is going to be 2t. Like so. And then you can just simplify it out like this. And you could just mostly leave it like this, apparently. Though sometimes they might want to ask to like have this only in terms of t. If it asks you to do that, then you're going to have to plug these in. In this case, we get into where did we have this? Yep. Plus 2 times this t squared. Where? No, it's 2t. What am I doing? 2t times t squared plus 2 times t squared times t. In this case, we have 8t cubed plus 2t cubed, which is equal to 10t cubed. Let me just go check if that was right. If that was right, I am not actually too sure on this one. Forty. 4t squared, it's 4t to the 4th. You should get 16. Oh, I'm an idiot. This should be 2t. It should be 2t. It should be 2t squared times t. Like so. So you get 16t cubed. And this seems to, and this is the right answer. The other way you could have done it was essentially you have the f of xy, and then you were to reparameterize this in terms of the x and the y, in terms of the t here that we have, where x is equal to 2t, y is equal to t squared. So you'd have f of t is equal to 2t squared t squared, which is equal to 4t to the 4th, and then df dt would become 16t cubed, which checks out with the answer we got over here. Though sometimes you just straight up cannot do this. Because here I gave easy functions and another easy function to work with, so it works here, but sometimes you just straight up can't. Alright. Tree diagram. One helpful illustration that is often used to make sure we have all of our partial derivatives and normal derivatives in check is a tree diagram. So if we have like an f here, we had x and y, and then x and y dependent on t. like so. We can say that this is the partial with respect to y, this is the partial with respect to x. This is dx dt, dy dt, like so. Let me just go make these. These all curly, because I keep forgetting to do that. So this is fairly useful if you have like a way more complicated function than just what we have here, which is just fairly simple, like one multivariable function where the functions are where x and y here are functions of another variable t. But if we had like something really bad like the one we had like earlier, I'm trying to remember what it was. Is something like this, then yeah, such a diagram would be really helpful for actually parsing this whole thing down into the chain rule, which is what we have over here. So yeah, be able to use the chain rule to find the derivative of composition functions of multiple variables. So this is just a chain rule of two independent variables. We're going to use 2 as a test case, but this could work for like multiple as well. So if we had like f of xy is equal to something, and then x dependent on, suppose, r and theta as an example, and y is also r and theta, then we have 2 derivatives we can get. The partial with respect to r, which in this case is going to be the partial f with respect to x, and then the partial times the partial x with respect to r, plus the partial f with respect to y, times partial of y with respect to r. This is going to be there's a very similar expression for theta. I'm just going to copy paste this expression and change a bunch. So these here, if we wanted to take the partial with respect to theta, we'd have this. Partial of f with respect to x, times partial of x with respect to theta, plus partial of f with respect to y, times partial of y with respect to theta. Yeah. Hello, whoever just joined. Alright, so let's say we had f of xy is equal to xy, like so. Oh, we had x is equal to r cosine theta, and y is equal to r sine theta. And suppose the question wanted you to find partial of f with respect to r and partial of f with respect to theta. Using our rule here from earlier, we'd have partial f with respect to x, which is going to be y, times partial of x with respect to r, which is going to be cosine of theta, plus partial f with respect to y. This should be negative y sine theta. Oh, no, it is y cosine. Times the partial of f with respect to y, that's just going to be x, times the partial of y with respect to r, which is sine theta here, because this is a constant. And then we can just do a similar thing for theta. Again, here's a formula. So first partial f with respect to x, that's just going to be y. And then here we have partial of x with respect to theta, which is going to be the negative r sine theta from earlier. And then we're going to have x for the partial of f with respect to y, and then r cosine theta, which is the partial of y with respect to theta. Which you could just rearrange to just say r cosine theta minus y r sine theta, like so. And that's about it for this. If you want to just plug in everything to get this only in terms of r and theta, you absolutely can. Alright, and that's it for 4.5. That's all the concepts we need. Section 4.6. This is directional derivatives and the gradient. So let me just start with directional derivatives. So suppose we had a function f of x, y, and instead of moving along just the x direction or just the y direction, we wanted to move in, suppose, a unit vector u, which was ux, uy, like so. The directional derivative along the unit vector of f of x, y is defined as the limit as h goes to 0 of f of x plus u of x h, y plus u y h, minus f of x y, all over h, like so. You can see here this is sort of a generalization of the partial derivative limit that we had earlier, which is over here. But in these cases, your direction was either I hat from the plus h here and holding the y constant, or j hat where we hold the x constant, and then y was being changed, like so. So this is sort of a generalized version of that. And there's actually another way to represent this that is often way more helpful. That is going to be way more helpful than just this limit definition. Here, and that's with the concept of a gradient. So the gradient is going to essentially be del f, like so, which is equal, which for 2D for two variables, which we have here, we're gonna have the partial of f with respect to xi plus the partial of f with respect to yj, like so, right here. This generalizes for any number of variables you want. It's just the partial derivative with respect to the variable times the standard basis vector, and then sum to all of them up. So in this case, our directional derivative from earlier, which I forgot to give the main way of doing that, which would just be the partial f of x times ux plus fy use of y, can also be expressed as the gradient dotted with the unit vector itself. And if you wanted to plug in a value, you would just have f of x naught, y naught, dotted with, again, the unit vector. So let's just have one example for this, in the interest of time, even though we've got a lot of time. Let's see, find the directional derivative of f of xy along u is equal to 1 over root 2. 1 over root 2. Now I'm gonna just give a unit vector. On the exam, you might also see, like just any random vector, 1, 1. If you get this, you must convert this to a unit vector first. At 1, 1, 2. So, using our formula, we have the directional derivative at f of xy. We'll start with f of xy first, and then just move on to f of 1, 1. Which is going to be the gradient of f dotted with the unit vector. So the gradient, we have the partial derivative with respect to x, which is just going to be 1, times the u of x, which is just the 1 over root 2. And it's the same thing here. Fy, which is just 1 again. And then u of y, which is 1 over root 2. So we get 1 over root 2 plus 1 over root 2, which is equal to 2 over root 2, which is equal to root 2, actually. So what does that mean for f of 1? 1, well, it's root 2, because we didn't have to plug in x and y at all into this. Now, if I had something more complicated over here than just x plus y, we would have to plug it in. Alright, know the relations between the directional derivative and the gradient. I already did that. Directional derivative from definition in the gradient, the definition, or from the gradient. We already have that. Understand the properties of the gradient and how this corresponds to this. Okay, so the properties of the gradient that we're interested in is the partial of f gives the maximum slope actually maximum, and let me just hold on, let me reword this better. Gradient of f is the direction of maximal increase. Negative of this is going to be the direction of maximal decrease. Let me just copy paste this. Like so. The magnitude of a gradient is the maximum slope the function attains. And let me see that. That's about it for this one. These are the ones we're mostly. Oh, one more. Gradient of f is the normal to the level curve, to a level curve. That's the final one we want. All right. Let me just go ahead and see if there's anything up in the chat. Okay, so normal to a level curve. So if we remember from earlier, the level curves are essentially where we had f of xy is equal to k. So in this case, or z is equal to k. So suppose we had some sort of function like this. Let me just go ahead and grab some extra colors. And that these were the level curves in question. And z is equal to 0, z is equal to 1, z equals to 2, you get the idea. And suppose you wanted to find the normal to the level curve at a specific point, which I have outlined here. This would be the gradient here, the direction at this point. You see how this is orthogonal to the level curve itself over here? This is what we mean by normal to a level curve. It's sort of normal to like this point here, like a tangent along this level curve, on the level curve. Like so. All right. So that's gonna be about it. But that was actually the only thing I needed to get done for that one. So section 4.7. This is actually probably the worst section of that we're gonna have on the exam because it's local and global extrema. Yeah, not that this section is like very, very difficult. It is just the most time-consuming thing ever, particularly with global extrema. Yep, don't worry. I also hate this section as well. Oh, if we're gonna have a global extrema example, I'm probably gonna make sure there's some other way to do it besides doing it the main way to do it, because it sucks. All right. Anyways, enough ranting about section 4.7 being horrible. Let's just go on to this. So the idea here is essentially we're going to go back to our partial derivatives from earlier. So suppose we have this is equal to some function. So in order to do this, we're going to have we had our first derivatives. We want to essentially find yep, this is getting recorded by all right. We essentially want to find the critical points like we did for regular extrema. So in this case, we want to find the points where either f of x equals to 0, fx equals to 0, and fy equals to 0, and all the points where one or the other is undefined. These are your critical points here. In order to classify these, we have something called the second derivative test. The second derivative test is where, unfortunately, we don't have anything better to work with, so we're just going to use D. So D is equal to fxx times fyi. My God, why did you have to crash at like the worst time freeform? Give me a second. It's minus f of xy squared afterwards. Where was I? Fyy minus fxy squared. And yes, technically this is also fxy, the fyx, but because these are equal to, either partial derivative of x and y is 0, or partial derivative of x or y is undefined. It's right here. Alright, anyways, if this d value is equal to 0, it's inconclusive. We can't really say anything at this point. If the d is less than 0, this is implying that these two here have opposite signs, so we're going to have a saddle point. Now, if d is bigger than 0, we're going to have two cases here. Oh, let me just go copy paste this twice. We're going to have the one where fxx is bigger than 0 and fxx is less than 0. Or fyy as well, but when we have d is bigger than 0, it's implying that these two here have the same sign. So here, we have f of xx is bigger than 0. We're going to have a local maximum. Minimum. Minimum here. And then we have a local maximum here. I'm going to go verify that one really quickly. I think it should be this. Where did I put it? Let me just go to my lecture notes. Where are we? Yeah. Yep. If it's less than 0, it's a local max. If it's bigger than 0, we have a local min. Okay. Cool. Be able to find global extrema on a given function on a closed bounded domain. This is gonna suck. I'm just gonna do one example right here, but considering I also hate this section pretty much as you guys, is I'm gonna have a backhand solution for this such that we don't have to worry about this. So I'm just gonna have x squared, let's say we had a function x squared minus 2x plus y squared minus 2y, and I ask you to find the absolute minimum on D is on this region D, which I'm just going to make this very easy and just make this a rectangular region. -3 is less than equal to, let me just use side notation properly. -3 to 3 and -4 to 4, like this. Okay, so the normal method, what you would do is you'd find your critical points, find where they're both equal to 0, and then you also have to check on every single boundary point. Every single one of these boundaries here. You have to make that into a line, and then you check along that straight line for the maximum or minimum there. And then you check against every single value you have for which one's the minimum and which one's the maximum. So thankfully, because I made this example, there's a better way, but don't do this for every single case. I'm just doing this so I can skip all the algebra for this. So, the way I engineered this to work here so that I can just skip a bunch here is essentially we're gonna have this right here is incredibly close to a square. If we just had a +1 somewhere, we'd also have we would have a square. Same thing with this guy. So I'm just gonna add them in and then subtract them off, like so. And then this is now gonna be x minus 1 squared, and then y minus 1 squared, and then we still have this -2 over here. This portion is always bigger than or equal to 0, because we only have square terms at this point. So our absolute minimum is going to be -2, because 1, 1 is inside our region. If you notice here, this goes from -3 to 3, -4 to 4, 1, 1 is in our region. So this is the absolute minimum, guaranteed. And it happens precisely at 1, 1. This will not work for every single one of them, as you have to be quite lucky in order to get this kind of structure or any other structure that would make this easy. And then it's inside and the critical point is inside our region. But I hate this section a lot, so I'm just gonna do this. And if you were to do this the other way, the normal way, hey, I can copy paste stuff. Hey, come on. We would first have to go to calculate fx and fy. In this case, we'll get 2x minus 2 to y minus 2. And then set them both equal to 0. You're going to get that x equals to 1 and y equals to 1. So our critical point is 1, 1, just like we had over here, with the 1, 1 on the squares. And this is our only critical point, since it has to occur over here. And there's no way for these to be undefined, since polynomials are typically defined everywhere. So at 1, 1, our original function is going to be -2, like we had earlier. And now comes the really, really bad part. We have to check every single line here. So let's just go through each one by one and just call this a day. So here we're going to go through a lot of x equals to -3, which is one of our boundary lines. So we can have the y move freely between -4 and 4, and then we're going to have g of y equal to f of -3 comma y, and then we're restricted between -4 and 4. And this is where things become pretty bad. I'm just going to use the square one. 1, we get -3 minus 1, that's -4 squared, that's 16. Minus 2, 14. Plus y minus 1 squared. This obviously has the critical... This one pretty obviously has a critical point at y equals to 1. I don't think so I have to go through too much of the math for this one. 1, you just get this over here. And then your maximum is just somewhere around the end points of this. Which we're going to have to check afterwards. We're going to do the same thing. 3 comma y. Which is just going to be 4, because we get 3 minus 1, that's 2. Plus again, a y minus 1 squared minus 2. This 1 squared, like so. And then h prime of y, this is just your 2y minus 2. Your critical point is y is equal to 1. And then I'm just going to do the same thing for x. Just give me 1 second to do that. X comma -4. We have x minus 1 squared. Plus 25 minus 2. Plus 23. X minus 1 squared. Plus 4 minus 1 squared, that's 3, that's 9. 9, and then plus 2, minus 2. Good. Plus 7. These have the same crit points of x equals to 1. One like so. And finally, we just have to plug every single thing here, including all the endpoints. This is -3 to x to 3. Alright, let me just go ahead and do this. G of -4, G of 1, G of 4, 4, H of -4, H of 1, H of 4, or I of -3, 3, I of 1, I of 3, J of -3, J of 1, and J of 3. And just calculate what these are equal to. For the sake of time, I'm just going to calculate these mentally. G of -4 square of -4, which is going to be 14 plus 25. That's going to be 39. Right? G of 1 is 14. And actually, I can just copy paste the h's to. H will give me 2, 23, and 7. And then G of 4 is going to be 23. Yep. H of -4 is going to be 2 plus 25. That's going to be 27. And then 11. I of -3, that's going to be -3 minus 1. That's going to be -4. 16 plus 23, which is also 39. And then I of 3 is going to be 27. J of -3 is going to be -4 squared, 16, 23. J of 3, 11. Hold on. I think I do have it, but I usually disable it.
Alright.
Let me just see. Have it.
Well,
Let me just see. Let me just see if I have a temporary marker thing. Or is it? Okay, shadow. Let me just see. Where the hell is it? Is it auto minimize? It's just give me 1 second. I'm just gonna check for what I have onto here. There are pencil gestures. See. Oh, got it. Looks like I got it. I just have to be pretty close to this. Alright, anyways. I have to be pretty up close. Also, otherwise it won't register properly. So I'm just going to use the cursor for this. So with all of this, we have that the absolute with minimum was just on a critical point, which was just the -2 from earlier, as all of these numbers are positive. And our absolute maximum, which is 39 by the looks of it. Yeah, this is just actual hell to do. Alright, we're just gonna... that is just Global Extremer for you. Let's just move on to section 5. Let's just move on to chapter 5 already. Alright. Section 5.1. We don't need that. Okay, so this was about the double integral. A double integral represents typically a volume under a surface, where the surface is defined by some function, and that is mostly what you have. If the function in question is a mass density function, the double integral represents the mass. This should be region, not function, region. And the height is defined by a function. So there we go. So, the double integral, if it's a mass density function, this represents the mass of a thin plate in the shape of the region. And finally, if the function is 1, the double integral represents the area of the region. Technically, if I can spell right, it is a volume with a constant height of 1 but for most purposes we will treat this as an area. As in area. Good. Alright, that is I think the conceptual understanding of the double integral. And as far as the definition goes, is we have this, which is really another limit definition. Yep, limit as n goes towards infinity. So n of, and then x of x of I, y of j, delta x, delta y. This often just gets abbreviated to delta a. Like so. And then this could just be a definite. This could be a definite or an indefinite. Really doesn't matter. These have the same limit definition right here. This integral gives a signed volume. So the volume can be positive or negative. It doesn't really matter here. And then finally it says be able to integrate fxy over a two-dimensional rectangular region. So a 2D, I can put it up here, rectangular region is one where x and y are bounded by constants. An example of such a region is going to be this region, which is all the points such that -3 is less than or equal to x is less than or equal to 3, -4 less than or equal to y less than or equal to 4. This is the same region we had earlier for that really bad absolute value problem. So, if we wanted to integrate over that, and we'd essentially just put constants. Because these are constants, it doesn't really matter which order they're in, but I'm going to just put them x and y. Like this. This is a double integral over region D. Like so. So, as an example, let's just suppose f of xy is equal to xy. Evaluate the double integral over the region D, which I'm gonna just copy paste this region over here. So in order to do that, we're gonna have here, we're gonna just set x equals to -3, 2, 3, y is equal to -4, 2, 4 of xy dx dy. Note here, Fubini's theorem says that you can swap integrals if the region, simply swap it, is rectangular. In the context of this means the order really doesn't matter. You could have done this, or you could have done the y first, it doesn't really matter. And then you just evaluate the innermost integral first, and then work your way outwards. So in this case, we have y equals -4 to 4 of, here the y is a constant, so it just sits there. And then we have x squared over 2 evaluated from -3 to 3. And then evaluating this guy, we have y 3 squared over 2 minus -3 squared over 2, which I just realized this is 0. 3 halves minus 3 halves dy. Actually, not 3 halves, 9 halves, or 9 halves minus 9 halves. And then you just get the integral from y equals -4 to 4 of 0. At this point, the y is also gone. And so you just get 0 at the end. What an example. Alright, and that's every single topic, actually, that will be on the exam. Okay, let's just move on to practice problems. Alright, we're going to start with the ones in the exam review, and then we're going to... Okay, so now that we're done on the topics, should we just do the ones on the exam review, or textbook problems, or what? What do we want now? We got through every single topic that will be on the exam.
I think the exam review would be good.
Alright, exam review problems? Alright. Alright, exam review problems. Number 1. Number 1 asks you to complete the limit definition for the partial derivative with respect to x. So I'm gonna just take this guy over here. Here, this is gonna be the limit definition for the partial derivative with respect to x. 1b. Assume that k is in the range of f of xy. True or false, the magnitude of the gradient of f is orthogonal to the curve defined by f of xy is equal to k. This is actually false because magnitude of a gradient does not have a direction. So, this magnitude being orthogonal to something does not make sense. C. This has two parts. You're hiking on a mountain where the height of the mountain is defined by h of xy. You're an avid hiker and you want to ensure you always hike in the steepest uphill direction. And it says to give an expression that determines which direction you should go at any point xy. So this is essentially just the property of the gradient of h of xy. Gives the steepest uphill direction. Direction. Number 2, while you're an avid hiker, your dog is not and does not want to go up or down. Give an expression that determines a direction at any point xy such that as you walk, you never change elevation. Okay, this one's a little bit harder. It's not defined simply from just a gradient. The idea here is we're going to have to rely on the directional derivative in the sense that it gives the rate of change of a function's output as you go along a direction. God damn it. U equals U of x uy. Give me 1 second. Give it 1 second. Okay, we're back. Ux uy. Like so. So, what does that mean for the expression? Our expression is thus going to be the gradient dotted with AB is going to be equal to 0 because we do not want to change elevation at all. And then we want where a squared plus b squared is equal to 1, just so that we can maintain a unit vector. And is the direction, oh, whoever just joined, where you do not change elevation. Awesome. So this is basically all of C. D. Consider a function f of xy, where x is equal to x of u comma v, and y is equal to y of u comma v. True or false? The chain rule for the partial derivative of f with respect to u is then partial derivative of f with respect to u is equal to partial f with respect to x times partial x with respect to u. So this is going to be false unless partial f with respect to y is equal to 0 or partial y with respect to u is equal to 0. Remember your chain rule. I'm going to make this look a little bit better. Chain rule says partial f with respect to u is partial f with respect to x, partial x with respect to u, plus partial f with respect to y, times partial y with respect to u. Like this. If any one of these two is 0, the original one satisfies this. But in general, this is false. E. Consider a function g of xy that is differentiable on a closed bounded region. True or false? The global maximum of g over d is always at a point such that either the partial derivative of g with respect to x is equal to 0 and the partial derivative of g with respect to y is 0. This one is going to be false. And to show why, I am going to show a counter example to whatever we just had. Let's suppose that g of xy is equal to x squared plus y squared. And suppose we had a region which is as follows. I'm just going to be very, very cheeky with this and just do the circular region. X squared plus y squared is less than or equal to 9. If we graph this, so our region here is just going to be a circle, like so. And then our function is just going to be doing whatever. This, as you can clearly see, this is where the maximum, or the global maximum, is. However, if you calculate the critical points, this is where the crit point is. This is roughly at 0, 0. Here is a demonstration here. G of x is equal to 2x, g of y is equal to 2y. Y set them both equal to 0, x equals to 0, y is equal to 0. So this here is roughly where your critical point is. But the global maximum is up here, which is precisely on where this boundary is. So this is false. Awesome. F asks you to list 3 conditions that must be true for a plane to be considered a tangent plane. So the first condition is your tangent plane at a specific point, at the point you're taking the tangent plane of, must be equal to the function at that point. This is straight off your lecture notes. The partial derivative with respect to x exists, and the partial derivatives of the tangent plane and the function are the same. And 3 is just the same thing, but for y. I'm going to just do that, and we are good. F of y, pi of y, f of y, like so. These are your 3 conditions. G. This one asks you to explain the definition of a double integral. So for the definition, the double integral what's a good word to use for this? I'm just going to say pixels, because it almost works as pixels. Of pixels of width delta x and height delta y. And integrates over this region of pixels. And let me just. And I'm going to say again. Oh my god. And multiplies the area of each quote-unquote pixel with the height. And adds them all up. So this would basically be like, in your own words, this sort of explains what a double integral does. It just slices in x, slices in y. Alright, that's the other way to do it. But I think this works. Alright. Let me just see if there's any questions. And then I'm moving on to number 2. Yeah, let me just go ahead and just reload Discord. Oh yeah, let me just go upload these notes. Let me just go ahead and just... Okay, looks like people want the notes up first, so let me just go ahead and just do that. Just go ahead and, since I think the first one seems to be a good one, and the rest are really okay, depending on it. It's just stuff we've already done before. We're at 3. Hmm. 4.6. 4.6. Alright, let me just go ahead. Let's see. Alright, the midterm notes have been sent. Alright. Alright, should we do more exam review problems, or should we just move on and just do textbook problems? Because honestly, the rest of these are just like stuff we've already seen before. And I think we've already done these to death at this point. Awesome, let's just go textbook problems then. Well, problem 1 is just like a good problem to go through, but the rest are just like, nah. Textbook problems. Right. Next up we got so first we have 3.3 number 103. I'm gonna make that a little bit bigger. Which says to find the arc length of the curve on the given interval. So r of t is equal to t squared I plus 2t squared plus 1, and then j. And then we have 1, t is between 1 and 3. So your arc length is going to be the integral from t equals to 1 to 3 of the magnitude of the derivative, which we're going to go ahead and calculate, which is going to be 2ti plus 4tj which is going to become, and then we have square root of 2t squared plus 4t squared. 4t squared plus 16t squared. This is going to be square root of 20t squared. Hang on, let me just go fix something up really quickly.
Should that simplify to root 20
Yeah.
times t?
Yeah, you could just do root 20 times t like this. So putting that up here, we have, oh my god, I keep forgetting to do these. And I'm just going to use the tau. Or just use like t1. Or I'm just going to use t1. Which is equal to root 20 times this t1 squared over 2. Evaluated from 1 to 3, which is equal to root 20 over 2, which is going to be root 5. Times 3 squared minus 1 squared. Which is going to be equal to 8 root 5. Right, next, 105. Here, r of t is equal to t squared plus 1, 4t cubed plus 3, and t goes between -1 and 0. R prime of t, 2t, 12t squared, square root of 2t squared plus 12t squared, root 4t squared plus 144.
Don't forget the
Get the what? 144 to the huh?
Oh, you didn't write t square. You wrote 12t.
Yeah, 12t derivative of 4t. Oh yeah, there's a 12t squared here, but I fixed it on the other one.
Yeah.
Yep, alright, got it. And I'm just gonna go ahead and just get a 2 out here. T squared plus 36t to the 4. And I can get a t out as well. Oh, so that's gonna be 1 plus 36t squared. And yep, that's gonna be exactly what I was supposed to do. Because now we get something easily integrable. 2t root 1 plus 36t squared. I'm just going to use t1s. U is going to be equal to 1 plus 36t squared. Du is going to be equal to 72t dt. So this is going to become, and then the u here, -1, we're going to get 37. Even holy moly, to 1. Of 1 over 36 root u du. I'm gonna go check if that's right. Yep. What is even going on anymore? Into 1, and this is gonna be just 2/3. 136, 2/3 u to the 3 over 2, from 37 to 1. And assuming I did all of this right. Yep, 2t t squared, 2t root 1 plus 36t squared. Yep, that's the right u sub. And yep, it's 37 to 1. 2/3, we're going to get 2 over 108, which is going to be 1 over 54, times 1 minus 37 to the 3/2. And that should be the answer of all the squares.
He's not expecting us to go further than that, right?
I don't think so. It just says find the arc length.
Okay.
All right. 115 and 123. There's 15, which says that this to given r of t is equal to 2e to the t, e to the t cosine t, e to the t sine of t. Determine the tangent vector t of t, capital T of t. So, in order to do this, we're going to first find the derivative. And that's actually going to be it, because we don't have to use the unit tangent. But I'm just going to do it anyway. We have 2e to the t. And then for this guy, we have a function of t times a function of t, so we're going to have to use product rule. Minus, and then e to the t sine of t, e to the t sine of t, plus e to the t cosine of t. Like so. I'm going to go find the unit tangent vector, because it only says tangent vector for whatever reason. And I see why it only had tangent vector. You know what? Screw it, I could probably figure this out. Squared plus e to the t cosine of t sine t squared plus e to the t sine t plus e to the t squared, which is equal to the square root of 4e to the 2t plus, and then we're going to FOIL this out, so we're going to have e to the 2t t cosine squared of t minus 2 e to the 2t cosine of t sine of t plus e to the 2t sine squared of t plus e to the 2t sine squared of t plus 2e to the t to the 2t, I keep making this, cosine of t sine of t plus e to the 2 cosine squared of t. Holy. Alright, now we're just going to simplify this expression as much as I can. So here I've got an e to the 2t cosine squared and e to the 2t sine squared, which is just going to become 1. Here we have minus 2e to the 2t cosine t sine t, and we have plus 2e to the 2t cosine t sine t. Those two are going to cancel. And then we have the same thing over here. No, 2e to the 2t should be just e to the 2t. So all in all, we get square root of 6e to the 2t, or e to the t root 6. So the unit tangent vector is just e to the t root 6 times this whole abomination over here. Alright, and that's going to be 115. Though it only says tangent vector, I still found the unit tangent one anyway. $123. Which is same thing, but they give us a much easier to deal with curve. Plus 5t squared minus 2j. R prime of t is equal to 3t squared minus 4i plus 10t j. The magnitude of this squared 10t squared we have 9t to the 4th minus 2 times this and 2 times these two, which is going to become 24t squared plus 16 plus 100t squared. 100 minus 24, that's going to become 76. And then your unit tangent which is going to become why did I put that? It should be 1 over. It should be 1 over that. It's going to be 1 over this whole magnitude times the original vector. Actually, no, it's derivative. This one. Like so. Alright, that's 3.3. 3.4 problems, which is 155. Let's see why that. 3.4, number 155. Which is r of t is equal to 3t squared minus 2i plus 2t minus sine of t j. So here we're just going to do the velocity. It wants us to find the velocity, so we have velocity is equal to the derivative of the position, which is equal to 6t I plus 2 minus cosine t j. And that's it. $157 asks us to find the velocity, acceleration, and speed. in terms of t. R of t is 3 cosine t, 3 sine t, and then t squared. V of t is going to become negative 3 sine of t, 3 cosine of t, 2t. A of t is where we do the same thing again, but with velocity. So negative 3 cosine of t, negative 3 sine of t, and 2. The speed is just the magnitude of the derivative, or the velocity. Negative 3 sine of t, 3 cosine of t, nine cosine squared of t plus 4t squared. We have a sine squared and a cosine squared. So we're going to have the square root of 4t squared plus 9 as the magnitude of the derivative, and that's it for 157. (163). The position function of an object is given by r of t is equal to t squared, 5t, and t squared minus 16t. The question asks, at what time is the speed a minimum? So first, let's go figure out what the actual speed this is here. So first, v of t, which is just going to be our derivative. And then our speed. Plus 4t squared plus 25 plus another 4t squared minus 64t. Keep forgetting to do these. Plus 256. So this is going to be 8t squared minus 64t plus 281. Now we're just going to find the minimum of this. So we're just going to do the derivative of this thing, which means we're going to just have to get this over here, which is going to be 1 over 2 root of this guy. So 64t times the derivative of the inside, which is going to become 16t minus 64. And then we're going to set this equal to 0. 16t minus 64 has to be equal to 0 because the numerator has to be equal to 0. 16t is equal to 64, and we get the minimum occurs when t equals to 4. Awesome. 4.1. Where the hell did I wrote 3 or 4 over here? Is everyone good with chapter 3, or should we do some more problems?
I think we're good.
Okay. Oh, the numerator part? Okay, because we have a fraction over here, we have the 16t minus 64. The only way for the derivative, which is this fraction here, to become 0 is if the numerator is 0. So that's why we have the 16t minus 64 equal to 0 here, and then we solve that for t.
Is it because of the root, or it'd be undefined if it was?
It's only undefined if the denominator equals to 0. What derivative on top? Oh, that's because we want to take... That's because we're essentially trying to find the minimum of the speed. Oh, the derivative, that's from the chain rule. The derivative of what's in the square root is from the chain rule here. If you remember chain rule here, d over dx is just f prime of g of x, g prime of x. So in this case, the derivative of this is just going to be 1 over 2 root of that square root times the derivative of what was inside. All right, okay, looks like everyone's good right now, so all right. All right, should I send this up? Should I send this up before we move on to chapter 4? All right, I'm going to send up the chapter 3 textbook problems. This is unfortunately meaning you're going to have to see light mode again. Maybe I should have put it to set system theme or whatever. No, not files. What do you mean I spend most of my time in the dark? I'm just reading. Oh no, it's just evolving. Okay, let me just go ahead. Okay. Question 1. All right, and of course the unfortunate portion of this for some people. Question 1 from exam review. What's going on over there? Oh, okay, I'm not gonna bother. All right, chapter 4. This is gonna be Chapter. Textbook problems. Alright, 4.1. We're going to start with number 5, which asks us to find the domain of the function given. Here the domain is just going to be R2. Since polynomials are defined everywhere. (4.1) number 7. F of xy is equal to 4 of y squared minus x. Here I'm going to set, we need y squared minus x to be strictly bigger than 0. So y squared is strictly bigger than x. So our domain is just going to be xy in R2 such that y squared is strictly bigger than x. Number 9. It's just R2 again. Number 11, which now asks us to find the range. (16x minus x squared minus y squared) has to be bigger than 0. So we're going to have this. The x squared plus y squared here has to be bigger than or equal to 0. So this can be at the most 16. Thus the range is between 0 and 4. Because we use the square root, which is going to be equal to 4. And the reason why we're using the square root is because it's trapped in the square root. So if at 16, it's going to output 4. 13 squared. This range is going to be negative infinity to infinity. Because if x is equal to 0, z is equal to y squared, which has range 0 to infinity. And if y is equal to 0, z is equal to negative x squared, which has range negative infinity to 0. So thus we've got the whole thing. 17. G of xy is equal to 4 minus x minus y, and it says to find the level curves at the given c, which in this case is going to be 0 and 4. So first let's just go through set g of xy equals to 0, so 0 is equal to 4 minus x minus y. And here I'm just going to move the y on around, so I'm going to get y equals to 4 minus x. Set g of xy is equal to 4. 4 is equal to 4 minus x minus y. Subtract 4 from both sides, we get 0 is equal to negative x minus y. And y is equal to negative x. And that's it. Number 21. G of xy is equal to x over x plus y. C is equal to negative 1, 0, 2. So I'm going to set g of xy is going to be equal to 0. Now this one you're going to have to be a little bit careful with. Yes, the numerator has to be 0 in this case as well, but we have one other condition here, and that is that the denominator cannot be 0. So the full level curve is actually just x equals to 0, such that, and y is not equal to 0. That would be our full level curve. Now I'm going to go set g of xy equal to negative 1. So if I multiply both sides by x plus y, knowing that x plus y is not equal to 0, we're going to get this. Now, for the sake of convenience, I'm just going to multiply both sides by negative 1. So thus we're going to get x plus y is equal to negative x. And then I'm going to go subtract x into y equals to negative 2x. And then we've also got to make sure that y isn't equal to negative x because of our restriction. Just give me 1 second. From before. Alright, anyways, set g of x, y equal to 2. Mostly exactly the same stuff from earlier. X plus y is equal to x. So 2x plus 2y is equal to x. 2y equals to negative x. So y is equal to negative 1/2 x, and that's going to be our level curve. (23) is the final one for this section. G of xy is equal to e to the xy, and we're given c is equal to 1/2 and 3. Set g of xy equal to 1/2. Set g of xy equal to 3. So we have 1/2 is equal to e to the xy. 3 is equal to e to the xy over here. So in order to do this one over here, we're going to take the natural log of both sides. So you get natural log of 1/2 is equal to xy. I'm going to rewrite natural log of 1/2 is negative natural log of 2. And then finally we have y is equal to negative natural log of 2 over x. Here we're going to do a similar thing, so we get natural log of 3 is equal to xy, and y is equal to natural log of 3 over x. No. All right. What is going on anymore? going on in the chat? Alright, anyways, we're done with 4.1. 4.3. Note to self. Do not have carbonated drinks right before you do a lecture. I'm probably not following that. Four out 3 time. Where are you? Alright, this is about partial derivatives. So here we have c is equal to sine of 3x cosine of 3y, and it asks us to calculate the partial derivative with respect to y. So in this case, this sine of 3x over here is a constant. So we're going to have the derivative of just this guy, which is just going to be negative 3 sine of 3x sine of 3y. Like this. I'm not going to do x because it doesn't ask for it. 121. This one has z is equal to ln of x to the 6th plus y to the 4th, and asks us to compute dz dx and partial z with respect to y. So we're going to have to use the chain rule here. So we're going to have 1 over the bottom times the derivative of the inside with respect to x. And the same thing, a very similar thing with respect to y. All right, what's the next problem? 123. Here we're going to have z is equal to e to the xy, and it asks us to do the exact same thing. Here it's the same idea, the chain rule. We're going to have e to the xy times the derivative of the inside. With respect to x, that's going to be y. And with respect to y, we're going to have x. And that's mostly it. Actually, it is it. That is the entire problem. 125. Z is equal to tangent of 2x minus y. Again, it's the same stuff from earlier. dz dx and dz dy have become... So we're going to use again the chain rule. So f prime of x times prime of g of x times the derivative of the inside. And it's going to be the same thing here. Like so. The derivative of tangent is secant squared. $129. This one gives you z is equal to e to the negative x cosine of y, and it gives you a point. And it asks you to calculate the partial derivative with respect to x at this point. So here, the cosine of y is a constant, so it's just going to stay. And then the derivative of e to the negative x is negative e to the negative x. And then the partial derivative with respect to x, evaluated at 0, 1. Negative e to the negative 0, cosine of 1, which is just going to be negative cosine of 1, because e to the 0 is 1. $131. Here, it gives us a function f of x, y, z is equal to 2 sine of x plus y, and it asks us to calculate the partial derivatives at the point 0, pi over 2, negative 4. Alright, at this point, I'm just going to put up what we have here. Alright, let's start with the easiest one, which is going to be f of the z, because 2 sine of xy is all a constant with respect to z. So we're just going to get 0. And then for fx and fy, we're going to have 2 cosine of x plus y. And the same thing for this one because of the chain rule. Two cosine of 0 plus pi over 2. 2 cosine of 0 plus pi over 2. Cosine of pi over 2 is 0, so we just get 0 on both. So yep, that is most all. Oh wait, we still have 2 more problems. 135. Which means that we're going to have higher order partial derivatives. fxy for z is equal to ln of x minus y. So first let's calculate fx, which is going to be x minus y, and then times the derivative of the inside. Just 1 over the value itself times the derivative of the inside. Now I'm just going to go ahead and calculate this with respect to y. So we're going to have -1 times x minus y squared times the derivative of the inside x minus y, which means we just get 1 over x minus y squared. And that's it. This is gonna be a bit. Number 143 minus 3xy squared z cubed plus 5x squared z minus y cubed z. Let's go. And the question asks you to find f of x, y, z. Let's just do this the manual way, because I can't do it very fast on here. 2x, y cubed z. Y cubed z is a constant. Derivative of x squared is 2x. 3y squared z cubed plus 10xz. And then this is a constant, so it's gone. xy. We're going to have 6xy squared z minus 6yz cubed. And this is a constant, so it's gone. Finally, we have 6x f of xyz, 6xy squared minus 18yz squared. And that's our answer. All right. Looks like there is a question here. Are you going to be online like tomorrow at all? Like for questions or anything? I think I could be. Though it could be more like, it's going to be more like probably in the morning. Because evening I have to head back to the dorm. So yeah, but you should be fine asking me anything tomorrow. All right, 4.4. Wait, that's 4.5. This is tangent planes. All right, 4.4, number 171. Z is equal to -9x squared minus 3y squared. And the point they give us is 2, 1, -39. So with this, we're going to find the partial derivatives. I'm going to use z x. This is equal to -18x. This is a constant. partial with respect to y. This is going to be negative 6y. We're going to plug in the point. Negative 30. We get negative 36. And negative 6. So our tangent plane is going to be z is equal to negative 39 minus 36 times x minus 2 minus 6 times y minus 1. And that is it. 4.4, number 173. Z is equal to the natural log of 10x squared plus 2y squared plus 1. 0.000. This is going to make things so nice. So, 1 over the value times the derivative of the inside. I just need to wait for this thing to load. X squared plus 2y squared plus 1. And then 20x. Partial of y is the same story. 4y. Now you happen to just get 0 because the numerator just evaluates to 0 on both of them. So your tangent plane is just z equals to 0. Number 175. If this is where things start to get a little bit more complicated, but not that much. xy plus yz plus zx is equal to 11. And the point is 1, 2, 3. So in this case, we need to actually solve for z. We don't have z given to us. So what I'm going to do is I'm going to go ahead and just move the xy to the other side since it's the only thing that does not contain a z. Then I'm going to factor a z. And then divide both sides by x plus y. Like so. Now we're going to go ahead and compute partial derivatives. This portion sucks because you have to do quotient rule. Or product rule, but with f of x and 1 over g of x. As some people don't like quotient rule. Oh, oh yeah, I do have Kahoot installed. I just don't have the time to sit. I would have to set one. I'd have to actually set one up for that, but I probably could get one working. But anyways, back to this. Low d high. It should be like this. Minus high d low. Square the bottom and away we go. Same thing with this one. Low d high. This should be not -1. This is be minus high d low. Square the bottom and away we go. Now I just gotta go ahead and simplify this. Or not. Now I'm just going to plug in the points. Which is 1, 2, and 2. So the bottom becomes 9. 1 plus 2 is 3. 3 squared is 9. And then we get 1 plus 2 times -1. Minus 11 minus 1 times 2, which is just 9. which is just 9. This should be -2. This should be a -2. And then this is the same thing here, -1 minus 9 times 1. This first one, we're going to get -6 minus 9 over 9. -15 over 9, -5/3. This one, we get -3 over 9. -3 minus 9 over 9. -12 over 9. -4 over 3. And so our tangent plane is equal to z is equal to 3 minus 5 over 3 times x minus 1 minus 4 over 3 times y minus 2. 4.4. Number 177. This is x cubed plus y cubed is equal to 3xyz. And then we're given a point 1, 2, 3 over 2. Dividing both sides by 3xy, we get x cubed plus y cubed over 3xy is equal to z. Back to doing more partial derivatives. I don't like this one. More quotient rule. This is... Bruh. Alright. This is the bottom, and then low, the high. Minus high. The low. Square the bottom and away we go. Alright. Low d high minus high d low. Square the bottom and away we go. Alright. Yeah, I'm not going to simplify that. And then we're given the point 1, 2. So the bottom here is going to be 3 times 1 times 2 squared, which is going to be 36. 3 times 1 times 2 is going to be 6 times 3 minus 1 squared, 1 cubed plus 2 cubed is 1 plus 8. That's going to be a 9 times 3y. That's going to be 6. Again, same thing. We have an over 36 here, 6 here. 3 times 2 times squared. That's going to be not 24. 12 minus a 9 times 3. 18 minus 54 over 36. This is going to be equal to negative 36 over 36, or negative 1. 72 for the other one, 72 minus 27 over 36. This is equal to 45 over 36, which is equal to 5 over 4. This is an equals. All right. And the final step of this, the tangent plane itself. 3/2 minus x minus 1 plus 5 over 4 times y minus 2. All right. That's 3 sections done. I'm going to go take a small break. We'll reconvene at around 4:10. Why is it clapping?
Why not?
Okay, fine. Okay, fair enough.
Woohoo! Yeah. Wait, Ruda, what are you going over?
We're going to go over every single textbook problem that has been recommended.
Oh shit! All right then.
All right, yeah, we're on break right now, so at 4:10 we're gonna reconvene. Check the recording. Okay, the recording's still going. Yeah, this is gonna be the way how it is until like 4:10.